5G infrastructure and technology, key components and enabling innovations. The successful deployment and functioning of 5G networks depend on several advanced infrastructure elements and technologies. These components are designed to meet the needs of modern communication, ensuring faster speeds, lower latency, greater network capacity, and enhanced user experiences. Unlike previous generations, 4G and 3G, 5G involves a substantial leap in technology, requiring new network architecture, hardware, and advanced software. Here we'll dive into the key components of 5G infrastructure and the technologies that enable it. First, core components of 5G infrastructure. A. Radio Access Network, ARN. Traditional RAN versus virtualized RAN. The Radio Access Network, ARN, is the part of the network that connects mobile devices to the core network. For 5G, there is a move from traditional hardware-based RANs to virtualized RANs, VRAN. Traditional RAN involves dedicated hardware like base stations that provide coverage to mobile devices. VRAN uses software-defined networking, SDN, and network function virtualization, NFV, to move control functions to the cloud, making the network more flexible, scalable, and cost-efficient. Cloud RAN. This is an evolution of VRAN where the data processing is centralized and deployed in the cloud, allowing for more agile and scalable network management. B. Small cells. Role of small cells. Small cells are low-power, short-range base stations that improve network capacity and coverage. They are essential for ensuring continuous 5G connectivity in dense urban areas, stadiums, airports, and other crowded locations. Deployment strategy. Small cells are often deployed in areas with high user density, improving the overall network's efficiency by offloading data from macro towers, large cell towers. They also provide additional capacity in regions where higher speeds and low latency are critical. Femtocells and picocells. These are specialized types of small cells designed for very localized areas, like within a home or a building, that provide 5G coverage and capacity for smaller clusters of users. C. Fiber optic backhaul. Importance of fiber for 5G. To support the high data rates and low latency of 5G, fiber optic networks are needed for backhaul connections. Fiber provides the high-bandwidth links that connect the base stations to the core network, enabling seamless and rapid data transfer. High-density networks. In dense urban environments, fiber optics are critical for carrying large amounts of data from small cells and other infrastructure to the main network core. Given 5G's reliance on ultra-fast data rates, deploying fiber backhaul becomes essential for high-performance 5G networks. D. Core Network 5G Core, 5GC, evolution from 4G. The 5G Core Network 5GC is a complete overhaul of the 4G core, offering greater flexibility, scalability, and control. Unlike 4G's centralized architecture, 5G features a disaggregated and virtualized core network, allowing more efficient handling of traffic and the integration of new services like edge computing. Network slicing. One of the defining features of the 5G core is network slicing, which allows operators to create multiple virtual networks within a single physical network. This allows tailored services, e.g. for industrial IoT or autonomous vehicles, that have unique latency, reliability, and bandwidth needs. Service-based architecture, SBA. SBA in 5G simplifies network management and increases agility. It allows for easier implementation of new services and the automation of network functions using standardized interfaces. E. Edge computing, reducing latency. Edge computing refers to processing data closer to the user on edge servers that are located near the base stations or within the network itself, rather than sending data all the way to a distant central server or cloud. This dramatically reduces latency and enhances performance, which is crucial for applications like autonomous driving, augmented reality, AR, and virtual reality, VR. Enhanced experience. By enabling low-latency processing and localized data handling, edge computing improves real-time applications, leading to faster response times and a more seamless user experience. Second, Key technologies enabling 5G infrastructure. A. Massive MIMO, multiple input, multiple output. What is massive MIMO? Massive MIMO technology is one of the key enablers of 5G's ability to handle large amounts of data and many simultaneous users. It uses large antenna arrays, often hundreds or thousands of antennas, at the base station to send and receive signals to and from multiple devices at the same time. This allows for massive capacity and better spectrum efficiency. Beamforming. Beamforming is an advanced technique within MIMO where the antennas direct signals in specific directions rather than broadcasting them in. This reduces interference, boosts signal strength, and improves efficiency. B. Millimeter wave, M-wave, high-speed spectrum. One of the defining characteristics of 5G is its use of higher frequency spectrum, notably millimeter waves, 24 GHz and above. These high-frequency bands provide a large amount of bandwidth, enabling ultra-fast data rates, typically over 10 gigabits per second. Challenges with MM-wave. While MM-wave provides immense speed potential, it has limited range and is easily blocked by physical obstructions like buildings or trees. To overcome this, 5G relies on dense deployments of small cells and beamforming technology to focus and optimize the signal direction. C. Network function, virtualization and software-defined networking, SDN, NFV. Network function virtualization enables telecom operators to virtualize network functions, e.g., firewalls, load balancers, routers, and run them on commercial off-the-shelf COTS hardware. This reduces dependency on proprietary hardware, enabling a more flexible and scalable infrastructure. SDN, software-defined networking, allows operators to programmatically manage, control, and optimize the network using software. SDN decouples the network control plane from the data plane, offering more centralized and dynamic control over how data is routed and managed. It is critical for supporting 5G's need for flexibility, agility, and optimization. D. Dynamic spectrum sharing, DSS, efficiency in spectrum use. Dynamic spectrum sharing is a technology that allows telecom operators to share spectrum across different generations of mobile networks, such as 4G and 5G. DSS enables operators to use the same spectrum for both 4G and 5G at the same time, enhancing network efficiency and speeding up the transition to 5G by allowing a smoother coexistence between the two technologies. Spectrum flexibility. DSS provides operators with greater flexibility in managing the limited spectrum resources available, especially in areas where the demand for 5G is still emerging. The use of AI and machine learning, automation and optimization. Artificial intelligence, AI, and machine learning, ML, are being deployed to automate network management and optimize performance. These technologies enable dynamic resource allocation, predictive maintenance, and real-time optimization of traffic routing and load balancing. Self-optimizing networks, SON. 5G networks are becoming increasingly self-optimizing, with AI-based algorithms adjusting the network in real time to improve performance, reduce interference, and ensure consistent quality of service, QoS. Third, private 5G networks, enterprise-specific networks. As 5G becomes more widespread, private 5G networks are emerging, particularly in industries like manufacturing, logistics, healthcare, and energy. These networks provide enterprises with secure, high-performance connectivity tailored to their needs without relying on public networks. Use cases. Private 5G networks are ideal for applications requiring low latency, high bandwidth, and secure connections, such as Industry 4.0, automation, robotics, and IoT, augmented reality, AR for training or maintenance, and autonomous vehicles in controlled environments. Fourth conclusion, the future of 5G infrastructure. The infrastructure required for 5G is a combination of advanced technologies, new architectures, and innovative solutions. The key technologies powering the 5G network include massive MIMO, millimeter wave spectrum, network slicing, and edge computing, all supported by cloud-native approaches like NFV, SDN, and AI/ML for network management. These technologies are critical in delivering on 5G's promises of ultra-fast speeds, low latency, and the ability to support billions of connected devices. As 5G networks expand globally, the infrastructure will continue to evolve, enabling new applications in smart cities, autonomous transportation, industrial automation, and more. The ongoing innovation in private networks, network virtualization, and advanced antenna technology will ensure that 5G remains a transformative force for communication, business, and society as a whole. Please like, share, and subscribe for more technology-related videos here at Comparison 11. Also write us what videos you would like to see in the future. Peace.